Maybe that works. Hello? 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 Yeah, I think it's here. Okay, thank you very much for coming. This is the second ESG event this year. Unfortunately, we only had 2 so far, but hopefully we can try and keep the schedule. So it's mostly my fault because I didn't manage to organize one sooner. So have you all been here before, or anyone here for the first time? So yeah, I guess everyone's been here before. So I'm really happy that we are having another social. There might be a few more people coming, maybe in an hour, half an hour. That's what I expect. So we'll have 2 talks today. One is already on the screen about MicroPython and CircuitPython. So we're gonna, Eduardo is gonna show you a little bit and explain a little bit how you can use this beautiful language Python to program hardware-centric systems. I might make a few more announcements later. So, but for now, since we are already a little bit late, and sorry to everyone who was waiting on YouTube to join us, welcome to you as well. I hope you're still there. So I will pass on to Eduardo now, and thank you so much again for giving the talk today.
So, yeah. Can you hear me well? On the mic as well? I think so, right? Yep. Yep. Okay. Hello, everyone. Yes. I don't like to. Yeah. No. See, no? You can hear me to the mic? Yeah? Okay, thank you. Sorry. Okay, so hello everyone. My name is Eduardo Torres. I'm going to talk a little bit about MicroPython, just a quick intro. What is it? How we can use it? Where is used? Some differences against, obviously, C, and CircuitPython, and other stuff. So let me introduce a little bit myself. So again, my name is Eduardo Torres. I'm an IT technician and mechatronics engineer. Even though I have worked mostly in the software side of things, I have worked also with some simple electrical design, mechanical design, product design as well. Currently working on the software architecture on Solidem. I have many hobbies, like board games. We usually gather here. I study music, I enjoy reading, video games, 3D printing, a lot of hobbies in general. A lot of hobbies that also work here in Hacker Garage, right? So overall topics where I want to cover today. Again, what is MicroPython? Some of the characteristics and limitations. We're gonna have a little demo with the Raspberry Pi board. We're gonna tackle on other ports as well. And I want to talk on where is it used. So there are some real world projects that are already in production, or where we can use MicroPython in some everyday projects. Again, a little demo, and we'll have some time for Q&A. So far, so good? So we're going to start with what is MicroPython? Well, it's an open source project. It works with the MIT license. It was actually was started as a Kickstarter campaign back in 2013. Officially deployed back in 2014. It is still in development, an everlasting growing community. With an incoming 2.0 version soonish. We don't have a really final date, but it's kind of planning to have a release date for next year, hopefully. There are many ports for it. Well, I'm going to talk about ports a little later, but basically what is a port? It's a compiled version on MicroPython for a specific board. In this case, for example, we're going to talk about the Raspberry Pi. Some more technical details. It is based on Python 3.4. This little sign means that it was originally based on Python 3.4, but it chooses some other features from Python 3.5, 3.x, and the common version is not based totally on the newest version of Python, but it chooses some specific features that it implements. It is compact enough to fit on and run on within about 256 K of RAM, code space, and at least 16K of RAM. It can change a little bit. This is it's not a very bare minimum, but it's kind of the minimum recommended by the MicroPython community. You can play a little bit with, with how you compile it and how you optimize it even. It includes already some of the big Python, I mean CPython functionality. For example, one that is very useful, an RIPL, basically the Python console that it includes. Some fancy stuff like generators, some exception, and even some kind of, well, closures. Not in the most pure sense of closure, but what Python takes as a closure, right? Any question? Nice. So there's already MicroPython. There's also CircuitPython. There's a kind of a big difference between them. Actually, CircuitPython is a fork of MicroPython. It is totally based on one of the very first versions on MicroPython. This first one, CircuitPython, is maintained and developed by Adafruit Industries. I think we already know something about them. They, sorry, they develop and sell a lot of different boards, sensors, even actuators, a lot of stuff, electrical stuff, right? So this CircuitPython was developed and is maintained by them, and thus basically all their products are supported by CircuitPython. They are not the same. They have been developed for a long time, both of them at this moment. So they do not share the core libraries, the core code, and therefore they are not directly compatible. They are a little different, but in terms of applying some of the stuff or working with, I don't know, sensors, motors, etc., they work very different. So they're not the same. I'm going to focus a little bit more on MicroPython in this talk again, but Frank comes with a little demo using CircuitPython, so we can see some of the differences. Coming back to MicroPython, it is available, already comes with a lot of the core libraries of Python. Basically, these are the libraries we already have with any part of MicroPython. These are not exactly direct ports of big Python, but very similar, right? So we can have more of the basic functionality that we usually use with Python, like the OS library or system. We can work with some arrays, CMAT, collections, even some regex stuff, socket, time, etc. This is already built within MicroPython. Basically, in all the ports, it will depend a little bit. Again, this is not exactly the same as big Python, but very similar stuff. All of this is optimized to root on a microcontroller. Also, MicroPython specific libraries. These have a little pin in it. Why? It will depend, the availability of this will depend a lot on the board you are using. For example, the network library won't be available if you're using a board, well, a port that doesn't have a Wi-Fi or Bluetooth connection, chip in it, right? In this case, I'm using a Raspberry Pico 1 without Wi-Fi, so I do not have that library. In the other hand, stuff like Machine or MicroPython, I think even the B3 is in basically all the ports, but this is MicroPython specific stuff that will depend in the port you are using. In contrast to this, which is in all the versions of MicroPython. Of course, there are some big differences between MicroPython and big Python, and I mean CPython. For example, there are fancy stuff, basically like inheritance and f-strings. They are supported, but they are very limited supported, right? So, for example, f-strings, they are just the format of the string. We cannot do operation with the f-strings, so very simple stuff. In the inheritance, we can do one-to-one inheritance, but I kind of multiple inheritance, but it doesn't work very well. So beware if you want to use it with the MicroPython, you can encounter some unexpected behavior. Obviously, all of this is very well documented with the MicroPython official documentation, but beware, it's not going to be the same. No PDB available yet, very important. It is planned to be available on the next incoming version of MicroPython. That's a very good thing. Some Dunder methods work very different. For example, due to the garbage collector that we have in MicroPython, The dunder method of del is not going to be working as expected. Other stuff like path, if I remember well, they do not work basically. Or well, the del one work very different. I'm gonna talk a little bit more later. But again, different behaviors as the big Python version. No direct support for abstract classes. What I mean by no direct support, officially by MicroPython, they are not supported. There are some third-party libraries that support abstract classes, but I mean, working with microcontrollers are the kind of virtual machine we have, they're not the same, the best option. So again, be wherever you want to use them. Other fancy stuff like type hints are not really supported, and what I mean with not really supported, they kind of are. I mean, you can have some type annotation within your MicroPython code, but the interpreter not gonna be enforcing the types you mentioned, or they're just very basic stuff like just the parameters of a function, but not custom types, etc., etc. And of course, some syntax changes. Not very big changes in the syntax, but something to consider. Again, all of this is documented within the MicroPython documentation, so if you want to use MicroPython more deeply, you can take a deep dive into the documentation and see some of the differences there. So we have key components of MicroPython specific stuff. We have the underscore boot.py and boot.py. These two are going to be working with the boot order of your MicroPython board. Your MicroPython board. The difference between the two, the first one, the underscore boot.py, is already embedded in the firmware you are using. You cannot really modify it. You can, of course, consult the documentation and the official code and see whatever it's doing, but you cannot modify it unless you are doing a custom port for a custom board. You can change it and, of course, compile it, and it's going to be within your firmware, right? In the other hand, we have the boot.py, which is run after the underscore boot.py. Hard to pronounce names, sorry. The second one is one you can create. You can put directly on your board, and it's the very first thing after the bare bones boot that is going to be run on your board. You can work here with initializing some devices, and, maybe some memory, extra stuff you have on your board. You can map it here, and it's going to be passed down to the other files. For example, the main.py, as the name implies, is the main file that is going to be run on your board. By default, this is what the MicroPython firmware looks for running. Basically, your main script is going to be living here, right? You can, of course, have different other files, like, well, you can separate between classes, other modules, third-party modules, etc. Everything can live on your board, but the main thing that's going to be running is, of course, the main.py, right? MicroPython introduces these special kind of files, which are the .mpy files. These are basically modules, MicroPython modules that are precompiled. Yep, they have a special format for the way they have to be compiled and the bytecode. And the thing is, this is already precompiled, so in terms of efficiency, it's very well implemented. And you can pass directly .mpy file, .mpy file to your board, and directly do a Python import. I don't know, import my library, etc. That's going to be working directly by your firmware. We have some package management similar to Big Python. We have mpy, well, micropip, sorry. Of course, it doesn't work the same as the normal pip implementation. It's not going to be looking for the normal repos of Python. It's going to be looking for some specific repos of MicroPython, or you can work with third-party libraries, third-party modules made by the community, or whatever. You can, by installing a MicroPython module is not exactly the same as pip or CPython, because paths, etc. It's basically just getting all the needed files for the module and passing down to your board. So MicroPython, it helps to gather that kind of files and pass it to your board. If you have a board without Wi-Fi or Bluetooth connection, well, basically always USB the connection, but if you have one with Wi-Fi functionality, you can pass remotely some libraries. Since everything is written in C99, if I remember well, you can extend, as well as Big Python, you can extend MicroPython with C code. There are some caveats there, but we're going to talk about it later. Any questions so far?
Have you tried to compile it yourself?
Not yet. Not yet. I was reading the competition for a port. No, I haven't tried.
Do you need to recompile it to extend it, or is it possible?
No, actually no. If you want to extend like the framework itself, well, you can recompile it and put it directly in your framework. You can create a module with everything in C or well Rust or another language, and compile it to your to the MicroPython needs, and it will be a module directly for MicroPython. You can do an import in MicroPython directly. There are other methods. I'm going to talk about them and some of the numbers for them. Yep. One of the main characteristics about MicroPython, well, and Python in general, is the RIPL, which stands for read, evaluate, print, and loop. Again, it's the Python console. And MicroPython comes with basically the same RPL as the Big Python. You can see you can start connecting to your board. Well, we can have help for the function we have. We can import directly the libraries. We have some suggestion, how to complete, how to indent. We can start working, well, doing some operation. We can have access to the special underscore variable, which stands for the latest results. Basically the same as the Big Python one. You can use it directly on your MicroPython board as the first boot. Yeah.
The REPL implementation have like an option for you to save everything that you put into the terminal and then create a file for that?
Yeah.
It does?
Yeah, it does comes with some flags for copy and pasting directly, or having your output and creating files for it. Directly from the RPL, you can start working with, for example, well, OS, sys libraries, passing to your files, creating logs, etc. And also you can work, well, load other modules, create other files, that kind of stuff. Yep. Some special tools that actually are pretty recent. When I started using MicroPython, this didn't exist. This is MP remote, well, MicroPython remote. It's a CLI tool. You can actually see here that I run the command MP remote. It helps to connect to your Python board. Basically, it comes with all the functionality for USB connection, UART connection, Wi-Fi connection. I'm not sure about Bluetooth, but basically, all the way you can connect to your MicroPython board remotely or via cable. You can use it directly here. There are other options as well. You can use directly a screen command, minicom command, whatever you use, whatever you desire. But this is a little, well, fancy. It comes with some extra functionality. For example, you can load one of your folders within your computer and map it for your MicroPython board to have access to. So you have some script that you made on your computer. You can map that directly on your board, and you can start reporting or copying them directly on your board. Of course, you can use it, just copy and pasting the files with the SSP, something like that. But well, it's easier or fancier. Of course, it provides access to all the different ports of MicroPython. That does, even you create a custom board, custom port, whatever, it will work right away because of the needs for a port. Also, very important, it provides control over the basic stuff on the bootloader. You can do some soft resets within your script or the console, and auto connection for the remote boards, like Wi-Fi. Now, very important stuff, performance. Of course, it will depend a lot on the implementation of your code, similar to having contrast to C, CPython, Big Python. It will change a lot how the Python code was written, right? It's never going to be the same one-to-one comparison between C and Python, of course. Luckily, MicroPython was think since the beginning to have high performance on microcontrollers. So there are a lot of many tips and tricks that we can implement either on your C code or your Python code to make it more efficient to run in your microcontroller. Also, something to consider, a poor library implementation or MicroPython it will be basically the worst case scenario to run on a microcontroller. You can basically take some big Python libraries, make it run directly, well, as directly as possible on your MicroPython board. They're gonna run, of course, but you will have very poor performance, right? It will run anyway, but it's not gonna be the very best scenario. Actually, some numbers. There's this code, Nayuki QR code generator. It's in GitHub, you can look for it. It aims to be kind of the best implementation for QR code generations for all the language you can think. Well, that's the just bit of the repo, right? So here we took the version of pure C and Python. Directly with C, running the code and generating a QR code, if I remember well, was for a simplest thing, hello world. It took about 11 milliseconds. Taking the big Python code and making it run directly, well, as direct as possible again in MicroPython, the same string, hello world, it took 1500 milliseconds. So there's a big difference between running directly C code and the worst case scenario in MicroPython. But the caveat here is, for example, if we create the library written in C to run in MicroPython as a model, it will have basically the same kind of performance as the one within C. Compiled to run as a model, or even in your firmware, whatever. There's another version here, which is but not copying and pasting the big Python version and making it just run on MicroPython board. There, as I said, there are many tips and tricks to make it more efficient. You can go as deep as the bytecode that's going to be running on your board, not how the interpreter is going to interpret your orders, the memory, etc., etc. And you can go as, in this example, will be as low as about 100 milliseconds, running just Python code. So again, kind of a big difference comparing to just pure C, but if you take your time, you read the documentation, you can go to very similar kind of performance, only running Python code. Well, MicroPython code, because they're not gonna be the same. Again, I didn't have a number for this because, as the previous slide mentioned, it depends a lot on your implementation and how deep you go in your code. But we can have very similar kind of level of performance with C and MicroPython. Now, where can I use MicroPython? Well, there are a lot of different boards, a lot of different ports. There is, of course, the PyBoard official board. This is the original one. It's kind of hard to get these days, but this is still available in the store. Of course, there are ports for the ESP family, some of the most famous. The ports for the Raspberry Pico family. The first one, second version, Wi-Fi, no Wi-Fi, you name it. Well, the next option, to be honest, I always forget which company that belongs for. Frisco? Is it Frisco? I don't know. The I.MLC. No, no, I always forget it. To be honest, it is there in the documentation, but I always forget it. I'm sorry about it. Some SMT, some the family, etc. These are the officials provided by the MicroPython community. I put an etc. with a pin on it because again you can create another port for your board, custom board, and actually some companies are already doing it. So these are the very official ones. You can create one for your own. Yep.
So you're saying that other communities are doing it. That means that the PyBoard design is open source. It's available.
Yeah. All the MicroPython code is published under MIT license. And there's all the documentation for creating your ports, for making better implementation of the code, how the firmware should be created, etc., etc. Everything is open source. And for example, if you combine some open source hardware like the Raspberry Pico and MicroPython, you can create your custom board, custom MicroPython firmware, and run on your own product, totally in MicroPython.
It's not as demanding as a Linux system, so you don't need memory management.
Exactly. It's way simpler for him. Yeah, way simpler in that case. Yeah, in this case, I have a Raspberry Pico. In simple terms, this open source hardware provided and developed, and I think also manufactured by the Raspberry Pi Foundation. There are two families already, the RP2040, which is the very first version, and the RP2350, the second version. Both of them have the board option for a board with and without wireless connectivity, Wi-Fi and Bluetooth. In this case, I have the simple one. Well, there are going to be some differences between the boards, but the very first one have a Cortex M0 Plus. Again, it's everything open source in this kind of hardware. But officially, it comes with some SDK, for C and C++, of course, but also the MicroPython port is official, and also maintained by the Raspberry Pi Foundation. Again, everything is very well documented for this hardware and the MicroPython side of things. It's very well documented and easy to use, to be honest. Well, we have a little demo. I think I better cover the slide first. Where is MicroPython used? Why do I have a pin there? Well, basically, there's a lot of in-house development, but well, the companies won't be telling you, oh, we use MicroPython or C or these technologies, right? So there are some talks. Some of my reference for this was some of the talks in Python conferences in Australia, if I remember. Well, Austria, Australia, well, Europe, and some other continents. A couple of companies were talking about their experience with MicroPython and taking it to production. So, well, we don't have like exact data by how many companies it's used, but some of them are using MicroPython. I can tell you, in my work, we use it in early stages of testing in firmware. So, well, we use it for other stages. Of course, we use other technologies, but we do use it. It is covered by some universities as part of the programs. This doesn't mean that they don't cover C or well other languages, but they use MicroPython in some universities. I have seen it used in some programs for master degrees even, maybe just for testing some stuff or start as a big first approach to the microcontroller stuff on some boards, but it is already covered by some universities, sorry. Again, a lot of companies have in-house development. Some of them are using MicroPython. Some companies like WebShare that distribute hardware, again, at the fruit, they have, well, mostly CircuitPython code, but WebShare, for example, that they provide a lot of displays, sensors, and other kind of boards. They have documentation official within C and MicroPython as well. You can take a look on their websites. And of course, hobbies, right? A lot of people design some custom stuff, etc. And also, I thought it was kind of funny. There's a Casio official product that is shipped with MicroPython in it. I do not have one. I haven't seen one in person, but in the official Wikipedia page, there's already one. Casio product running MicroPython directly. A couple of examples. Think Transit, if I remember well, this is an Australian company. Yeah, well, not sure, sorry. They design a lot of, different solutions for monitoring, monitoring assets in general. They develop software and hardware for their clients. One of their main products actually is this little device here, which, well, of course, we can see the internals or anything else, but it's a custom board, custom design, and it's running MicroPython firmware in it. It is, of course, IoT enabled, supports multiple protocols, and I mean a lot of protocols. They talk about, of course, the usual one like E2C, IQBC, SPI, some GPS stuff, something like SCAN. I don't remember all the names, but they support a lot of protocols, really. And of course, integrate with other technologies, with other partners, other products for other companies. And this is in production already. For some years, actually. There's you can see the logo very well. Lumos Diagnostics, this is an American company. They develop some medical devices. This little device here is actually one of the examples. Again, they develop mostly the firmware for the board, not much on the electrical design, but it's an own product. This is actually complied with all the certifications that a product needs to have for a certified medical device. So maybe we can have different levels of performance against other kind of languages, but it can comply with some very strict certifications for even a medical device. These specific devices is for detecting, well, I don't know the correct terms, sorry, but it's for detecting and reading pathogens in different kind of readings, giving some kind of, not final conclusion, but some the reading for a doctor to use and continue with some diagnostics. I implement even this one image processing. I'm not sure at what level, if that is everything, but I'm pretty sure it uses another stuff. But again, this has been in production for some years. They actually provide still some further development to extend the functionality to maybe other pathogens, work with other partners, so that kind of stuff. I have, well, that's my last slide. Some useful links: the MicroPython official site, MicroPython documentation, and of course the Raspberry Pi official site. You can find a lot of documentation for the board, the hardware, and the software side of things within the Raspberry Pi official site. Any question? Yeah. Oh, yeah. You want, yeah. Mm-hmm.
I just want to know, I guess that you will need to have some kind of file system in order to be able to run those scripts.
Yeah.
But the microcontroller needs to be supporting those file system, or the MicroPython is going to provide you support for them? And if that is the case, which file system are supported?
Well, you run within kind of a virtual environment, of course. Basically, the MicroPython firmware is going to be handling all of that.
Okay.
In the documentation it leads, of course, how everything is loaded, the file system, how it is mounted, basically.
Okay.
Again, it's kind of a virtual environment, but the firmware need to handle all of that information.
Any more questions?
Hey.
Yeah.
Thank you.
So what is the environment that you use for programming for the Raspberry Pi? Do you use like Tony? I think it's the name, or which IDE do you use?
Yeah, that's a very good question. I didn't talk about it. Thank you. You can use whatever you want, to be honest. Since it's an interpret language and it's going to be interpreted in your board, actually, you're not running your code in your computer. Well, you can have kind of a web environment, I think. I can try some stuff, but you can create your files in, well, I usually use Beam, to be honest. Just create your files, you connect to your board. Yeah, sorry, I'm a little old school. You create your file, you send to your board and run on your board. As you mentioned, Tony is kind of the recommended IDE or environment from the Raspberry Pi Foundation. Why? Because it comes already with some of the tooling for communicating with your board. But again, the MP remote tool that is, well, was developed and is still maintained by the MicroPython community, it was developed exactly for that. You can develop your scripts, code, and even your framework in whatever environment you want. And with this tool or other kind of tooling, you pass your files to your board and run directly on your board. There are some official official plugins, for example, for VS Code, and in PyCharm, for example, provides a plugin that is going to be helping with auto-completion, some of the specific MicroPython keywords and functions that come with it. But again, you can really program in whatever you want, terminal if you want. Yep.
I guess the next question after that would be, I guess the next question after that would be how difficult, because you said that there were some like syntaxes differences and some like specific keywords that MicroPython includes that the regular Python doesn't. How hard is it to adapt when you're coming from developing in Python?
If you're coming from Big Python, it's basically one-to-one.
Yeah.
You're going to encounter some differences, of course, in usually the fancy stuff of Python. Again, like f-strings, multiple inheritance, some dunder methods, as we mentioned. Some dunder methods. After classes that are not there, if you use type hints, not everyone use type hints. But usually within the more the deeper stuff with Big Python, it's not going to be the same. But with the basic stuff and the stuff you need to start working with is one-to-one. If you start encountering some of the issues and when you're running, you can go directly to the documentation, and they have been doing a pretty good job documenting the difference in the version of Python even. So it is based originally with Python 3.4 version, but they document the difference within 3.5, 3.6, etc. So you can see the big difference. And even they have a whole section for the difference between Big Python and MicroPython. Yep.
Can you run a web server?
Sorry?
Can you run a web server in MicroPython?
Actually, yes. Yes. For example, on the Raspberry Pico board with Wi-Fi functionality, you can create, of course, MicroPython will have the network library with it, even the socket one, because it's part of Big Python. So yeah, you can start a very simple web server, even some, sorry?
Very primitive.
Yeah, very primitive web server indeed, but you can create one and connect with from your, I don't know.
I think it's something like Flask, maybe? I don't know if that runs.
I haven't tried Flask. I did try, again, with very simple socket functionality, just connecting and actually logging information. So every I think it was 30 minutes, the MicroPython board will connect to my Wi-Fi and log some information. So yeah, you can handle all of that within your board, or connect to your board, of course. So yeah, because again, there are some big Python libraries provided, and some specific to your port. But yep, you can run. If you have the hardware, you can run. Yep.
Do you
Yep.
have
You will have another question.
David, yeah.
Do you tend to run into like memory limitations if you're using like a lot of exceptions or deep call stacks, things like that?
Yeah, well, those are kind of the big differences. You can have, for example, coming back to multiple hindrance, or the garbage collector. Especially the garbage collector works very different with the big Python and MicroPython because, of course, the limitation within the hardware. Within the backtrace and how the environment is mapped for your path variable, for example, yeah, you can have like deep routes from your path and call trace, for example. Even in the if you're handling exception or watcher, real-time watcher, which you can set in MicroPython, yeah, you're kind of limited on how much space memory you can take. Again, everything is documented. Any other question?
Any more questions?
No question?
That's
No.
Yeah,
Yeah.
just something additional. Did you mention that MicroPython is kind of open source?
Yeah.
Which license it is using?
MIT.
MIT.
Everything
okay,
is under MIT license, yeah.
Okay, great.
And most of, that applies for all the core libraries, firmware ports and official ports, etc. For third-party ones, they usually follow the MIT as well. That one, of course, depend on them, but they usually follow the same. And it's everything on GitHub, Anthony.
Eduardo, do you want to give a demo or?
It's a very simple one if you want, or you can.
I can also do one. Should we do two, or would you like to start, or should we just do one?
We stop?
Yeah, we can do that, sure.
Okay.
First of all, thanks very much to Eduardo. That was really great.
Thank you.
So, just 1 second, we're going to change computers. Very nice.
All yours. I have the mic.
Yeah. Yeah, sure, do that. So we're going to say a bit more. Danielle is just going to show some advertisement for JConf. So not this Saturday, but the Saturday after is going to be the JConf conference. And there's some really interesting talks. There's still tickets left, and I think Danielle has also a discount code if you still want to go, because all the early birds are now sold out. But there's still a few discounted tickets specially for you if you'd like to.
Special discount code for this community for embedded systems. So I'm not quite sure on what's the percentage.
Yeah.
I'll let you guys know. I'll either way share it right now. I'll share it with a friend and you can share it.
Yeah. So it's really good. I mean, you get T-shirts, you get nice food. There's going to be a party. Really interesting talks. There's a couple of Java champions talking. I'm also giving a talk. But so it's going to be very nice. So I think it's about 300 people who already signed up for it. And it's a very nice event for networking as well, if you'd like to join. So let me just see if I can connect. Are we getting a signal? Nope. I'll try another adapter. Maybe that works. Yeah, it's a bit strange. Some of these work, some don't, but hopefully I can manage somehow. See? That's strange. No signal. I don't know if I have to say anything on the machine, but that's good. Okay, that's great. So thanks very much again, Eduardo. Yeah, thank you so much for the talk. I think it's very interesting to see that you can actually use Python to program a microcontroller. I mean, Python is not, Python is an interpreted language, so it's not the first thing that comes to mind. But I don't know if anyone went to HackGDL. There was one team who actually used MicroPython to do a save, to control a lock for a save. That's very interesting. And nice thing about Python is that you can just hack things together very quickly. It's a very nice language for kind of projects where you just want to prototype something. And yeah, you mentioned also it's used in some more serious applications as well. So I just want to give a quick demo how that actually looks in practice. And it's a bit of a hobby, so I have played around a little bit with MicroPython, actually CircuitPython. I bought myself a little microcontroller, which is the same one you see there. It's the same company that you mentioned already, Ada or Adafruit. And this one is really nice because it has some additional features. So this is not a standard RP2350. It's got additional RAM because the RP2350 only has about 510 or 20 kilobytes of SRAM. So this is a serial PSRAM as well. And it has HDMI. But this is for a different time. So actually the new RP2350, sorry, can actually produce HDMI signals. And it's really difficult because they are high frequency signals. You need much higher bit rates to produce these kind of signals, but it has some special features that allow you to do that. So I just want to show how can you control this thing. So the first thing is to forget about the HDMI. I'm just going to plug it in. Oh, it's just screensaver. It's just disappeared. And let's see if that works. So I'm just going to plug it in. And the first issue we have is how do we talk to it? Just 1 second. I think this is a bit. Try the other way around. It's always a problem with these boards that they are flipping over easily with a cable. Put something on top. Yeah, that holds now. So I've got a shell here, a terminal. And let's go into here. And when you plug it in, it kind of shows itself. So if you look into devices, and we look in the TTY devices, so we've got a USB modem here, which is a bit strange. It's a USB modem 101. I thought it would have been a different name, but I can easily change that. So we can, it's a serial device, and we can directly connect to that serial device and talk to it. So there's a screen command that Linux and Mac has, and I'm just using this command because it's available everywhere. I'm not using like Minicom or anything like that. The only thing I need to do is to slightly change the script I'm using to talk to it. So I've wrote myself a little script here, and that hard codes the name of the device. And since the name has changed, I'm going to change that here as well, and just see if I can get a connection. Yes, it works. So I'm not actually running MicroPython on it. I'm running another program on it, which just echoes back the thing you're typing. So it's a simple program. You ask a string, and then it tells you what the string is. So I can say Hacker Garage, and then it says that. So right now, there's not MicroPython running on it. But what I'm going to do now is I'm going to upload MicroPython on it. So in order to do that, you need to put the board into a boot mode. And in the boot mode, it exposes itself as a storage device where you can directly copy an image over. So to do that, I just have to press some buttons. And now I see if I can see it. So in volumes now, I have this RP2350. And that's the device where I can upload images. So I'm already having an image here, which is the image I downloaded for MicroPython from this site. And this is a specific image for this board. So if I now copy this to volumes RP here, so that takes a little bit of time because it's quite a big image. Let's see what happens. But I hope eventually it will work. With the old Pico, there was a problem. When you wanted to put it into boot mode, you always had to plug it in and out. That's a really annoying thing. With the new boards, you can do it over the buttons. So it seems to have finished. And if everything works well, we have MicroPython now running. And as you can see, we get now something else. So the serial port is still there. We can still talk to it over the serial. So it's a USB, it's basically a USB interface that emulates a serial modem. And we can talk to it directly through the terminal. I can make this just a little bit bigger so you can see it. So this is still there. But before we are doing this, I just want to show how we're interacting with the CircuitPython. So there's basically two ways to interact with it. We can directly enable the REPL loop. So here I'm in Python, and I can say something like print hello, whichever. And it's actually running Python on the board now, and I can directly talk to it. But I can also write some code. So for instance, when I reset this board, let me try and reset it. Now this is a script that tries to reconnect. So this is the equivalent actually of what you mentioned with the MP remote. But I have wrapped it into 20 lines of shell script. So it's doing the same. So it continuously tries to reconnect. But we cannot actually see it is doing anything. And what it usually does when you reset it, let's have a look. So in volumes, we have now a different drive, which is a CircuitPython drive. And this is where you can put our code. So it's very convenient. When you plug it in, CircuitPython exposes this device both as a serial device and as a storage device. And as a storage device, you can directly edit the Python code that runs on the board. So you've got the CircuitPy device, and I have some code here. And I can now, let me see if I can have everything here. I have an editor now, and that prints hello world. It doesn't show it within the output here, but it does show it if I connect it to HDMI. So maybe I could try and do that. So does it show it here? No, it doesn't show it here. But what we could try is to connect it to HDMI and see what happens. Now I don't know if the signal, if it picks up the signal, but we can try it. It might work, it might not.
No signal.
Yeah, it might have trouble with the resolution, because this device runs on a very low resolution. Yeah, so we got something here, and you can see this is the code that I just showed you that runs. So the nice thing about this Pico is that it has HDMI. Now, I could do a whole talk about HDMI on the Raspberry Pi. People have actually managed to do that even on the old version of the chip, the RP2040. But it's really hacky. I think I haven't seen that, but the problem with digital video is that you need a very high, as I say, bit rate. It's a digital signal. So with a VGA signal, you have one pixel, you have a pixel clock of 25 megahertz if you have a low-res signal, like 640 times 400. 25 megahertz is doable, because the Pico runs at 133, can even overclock it to 200, so 25 megahertz is with the POs that it has is doable. But when you go from analog to digital, multiplied by 10, because you need 10 bits per pixel. So it's 8 bits for colors plus 2 bits for TMDS encoding. So there's a certain kind of balanced encoding so that you don't have large sequences of zeros and ones. So, but with the new chip, they have a peripheral here, which is the HSTX interface, and that can generate bit rates up to 300 megahertz. And that's why you can use digital on this. It's still a bit tricky because you need to generate the right kind of signals. They're using certain signal standards. It's called differential signals. But it does work. So now, what I showed you in the terminal now, I'm also got it here. Let me see if I can just put the screen down a little bit. I think this has a button here, right? No. No, I want to put it down. No, I think I'm already, I mean, you can't see quite the prompt. If you're in the front row, you might just see the prompt here at the bottom. So that's possible. And I can directly interact with the Python from here as well. So I can say again, print hello or something. The only downside is, and you see that this is printed there, is that you cannot directly interact with the program. Because once I go into the REPL loop, it forgets about the program. So you cannot actually interact anymore with the stuff and the variables and the environment that you had before. So I can show you just something quick, and I'm going to embarrass myself because I don't really know how MicroPython works in detail. But so when it gives you a kind of hint. So you have this, and that's the last thing I'm going to show because Sid also very kindly prepared a talk, even in Spanish, and we want to see that talk as well, for sure.
I'm not going to give it in Spanish.
You're not going to give it in Spanish?
No, just English.
In English, okay. No, that's fine then. No, English is good for me.
Give it in Spanish.
No, English is good for me as well. Okay. So there's a way that we can actually see the different components. Usually it says that somewhere. Press feather, hello. Oh, that's weird, it doesn't say that. But we can, what happens if I type help? No. Yeah, it says something. Modules, so I have to say something like help modules, isn't it? Help modules. Let's see if that works. Yeah. So this is a lot of the different modules that are available, and Eduardo already explained, but these are, you have a few more here also because the particular version. So I can import the board, and I think the board, let me see if this works. The board has various definitions, so we have an LED here, and I can create a digital I/O for that. So and for this, I need to import digital I/O, I think. And now I can say LED equals digital input output board.led. No, it's called digital in out, I think. That's what I mean. I haven't really used. No, I just made it just a type here. Yes, I need to prefix it. Yes, of course. Yeah. So now LED is defined, and I still need to set the direction. So I don't know how to do this. I think it's LED direction equals digital I/O direction dot output, or is it just output? Yes. So now the LED should be accessible, and it acts as a variable. So I can just say, that is better. I can just say LED.value equals true. And I don't know if you can see that.
There you go.
So yeah, it goes on. You can say false, goes off. So this is just a very quick demo how you interact with the Python. Of course, I could put the same into a file that I just had. So instead of this, I could put all of this into a file here. And I could say, let me just see if I can find the same code. And I can copy it. Let me just copy this here. And I think I need to import the board. I need to import digital I/O. Then I've got the LED here. Then I need to set the direction. And I think that was the command for it. And then I can say LED.value equals true. And let's see if that happens, if that works. So the thing is, when I save the file, it should automatically restart. I don't know if that works now, but I'll see if that works. Nope. Then I have to reset the board. Let's try that. Well, is it doing anything?
It says code running.
Oh, that's weird. I would have hoped that it's code still running. That's strange. So
Maybe they didn't show anything because there's no like print output. Are you just turning on and off the LED?
no, I'm just turning it on, but I'm not quite sure why.
Yeah, probably you need to be in a loop or something like that because the code is.
Yeah, when it goes. So maybe I'd see what happens if I do a while true pass, something like that. Yes. There we go. So we can actually even make it blink. So what we could do is we could do this. We can set it to true. And I think there's a library for delays. So we can say something like time and time.sleep. I think it's something like that, half a second. And we say false. And now I'm going to save the file. And I don't have to do anything. That's a nice thing. When you save it, and you can see that it actually blinks. Kind of, yeah. So if you want to get this board, I mean, you can do the same thing with a normal, Pico that you buy for $5. This board is a little bit more expensive because of the HDMI, but as I said, you don't need the HDMI. So if you, for instance, I can show you that everything that you see on the screen here is the same thing that you also see. Let me see if it picks up the signal. You see the same thing here. So the HDMI is really just a bonus in some ways, and you can do more fun stuff with it if you don't use Python, something like that. So I think that's it for now. I want to just quickly, yeah?
Could you share the link to that board on the group?
To what?
The link to the board, like by board.
Yes, I can do that. I will post that on the group. And maybe if some like to have this board, we could also make a bulk order. Maybe it's cheaper. I mean, the problem with Adafruit is they're using DHL to ship to Mexico, and DHL are the worst kinds. I mean, the fees are just enormous. You pay half of the money when you order with DHL for shipping costs and processing costs, not for import duties. So, Danielle, do you want to say anything more about JConf?
Yeah. I just got in contact. Okay. Sorry. I'm interrupting here. Hi, my name is Daniel. Yeah, just wanted to let you all know that the discount is 50% off. If you guys are interested in going to JConf, there's food, there's beer, there's a lot of JVM related talks. A lot of the talks aren't about Java itself. It's more anything that has to do with the JVM. You'll be able to see Frank give his talk. He'll be giving a very interesting talk. I don't remember what the what's the name of your specific talk. I've seen it, but I don't really remember what's the name of your specific talk.
I'm just looking at the talks. So these are the JConf talks. I know these are.
That's a ticket. Just go to jconf.mx and there you go. There we go.
This is a program, and it's maybe a bit small. Let me see if I can make this a bit bigger. And yeah, you see there's a lot of different talks. I think this is the talk that I mentioned, but there's also Java champions here that are giving talks.
Yeah.
Talks about the JVM, and there's networking events, and we will have a party afterwards. So it's a really nice getting together.
There will be a party. As you can see, Frank right there is giving a talk. I'm giving a talk about the anatomy of the JVM. It'll be really interesting. Hopefully you guys can go, and if you guys are able to go, I shared with Frank the discount code. You guys can use that at checkout, and hopefully I get to see you all there. It'll be really fun. And side note, I brought you all some beer just because I'm coming as incognito, and I really like this community. I think you guys talk about really cool stuff, so yeah. Bye.
Thank you. So thanks so much, Daniel, for that. We'll have another really interesting talk. Sid probably needs 5 or 10 minutes to get ready. Meanwhile, help yourself to some beer. Help yourself to some beers. We have a lot for the group. You can have at least 2 if you want. And we'll be back with you on YouTube as well in 5 minutes. So Sid, I'm going to make some space for you. And just give you the HDMI. Which one? Doom. No, Doom. Next time, yes. We should do that. It's probably possible to do that. Sid, you don't need any adapter or something like that, no?
Pardon?
You don't need like one of those, no?
Need anything? No, I don't need
You don't use don't use
Sí,
this.
sí, lo resolvemos. Entonces, siempre más que lo gusto, ¿verdad? Entonces, sí. Yo sería más fácil. Bueno, normalmente el Power MicroPython va hacia las características de tu
You can. This might fit on your shirt as well.
Okay.
Ah, this is yours. Just give it 5 minutes and then we start.
Sí, tendría acceso al mismo. Sí, bueno, sí. ¿Qué digo yo ayer?
Hello? Hello? Can you hear me? Hello? Can you hear me? Hello? Not a speech. It's a presentation.
Son tres números y te lo hacen directamente. Puedes usarlo tú, pero ya tenemos estructuras por CircuitPython. Era lo que quería mostrar. Sí, está aplicando. Listo. Muy práctico.
Look at that backpack, Mila. That's pretty cool.
Para probar antes de pasar a otros estudios. Pero justamente los tiempos que se desarrollan acá se probaban
So, what's wrong with the air conditioner?
I think it's broken somehow. I don't know. I
Could
don't
be
know
just a
exactly
breaker?
why. I think so. Somebody explained it to Frank, but I didn't hear it well.
The kitty cat. ¿Qué dice niño?
He want me to take it from my videos.
No, it'll be online. I could send him a link. sent it to you and Nino. Here. What about a fan? I should run to the bathroom real quick. Should I take this off? I don't want them to hear me in the bathroom.
See what time it is. 3 minutes. I just go to the toilet.
what we need here.
So let's continue. Are we on YouTube again? Let me see. Okay, so sorry about that. So the next talk is given by Sid, and it's a little bit different from the previous one. So Sid's talk is about simulation of circuits. So that is an area which has more to do with hardware than software. And as hardware engineers, of course, you are interested in how to build circuits. Because at the end of the day, it's the circuit that makes the behavior. Every chip is nothing but a circuit underneath. So I'm going to pass over to Sid. Thank you very much, Sid, for giving this talk, and really looking forward to it.
No problem. Can everybody hear me? Yeah. Okay. Okay, my talk today will be on QSPICE. Okay. So what we're going to talk about today, first I'm going to cover QSPICE, the benefits to embedded system designers, the short history of SPICE, other SPICE products that are out there, the advantages and the requirements for SPICE, mixed signal example. I'm going to go through a few examples. Mixed signal, digital signal example, what's called a hierarchical or an embedded circuit example, and then another hierarchical embedded C++ example. And then last, we're going to cover a new device example. So who's this guy talking to you right now? I'm a retired U.S. Postal Service manager, 27 years. At the U.S. Postal Service, we work in maintenance on high-speed mail processing, sorting equipment, computer networks, PLC programming, for all different kinds of equipment that sorts letters, packages, flat envelopes, all kinds of mail. I also have a master's in business administration with Keller Graduate School of Management back in '02, with a concentration in project management. And I also have a Bachelor of Science in Electronic Engineering Technology with DeVry in Chicago back in 1983, long time ago. Okay, so everybody's probably wondering, what is QSPICE? Does anybody know what QSPICE is?
No.
He knows.
I think I used it once in like an electronic simulator.
Right.
It helped me define like an electronic part. I think I was trying to, I think it was some type of special, I don't remember what it was. It was something special that one of my teachers asked me for, and like I defined it in SPICE, I remember. It's
Okay.
been a while.
Okay. There's a big explanation. QSPICE is a circuit simulation tool that can significantly benefit embedded system design by improving the accuracy and efficiency of simulations. In a nutshell. So QSPICE for embedded system group. Okay, the QSPICE was created by this man, Mike Engelhardt, who also created LT-SPICE. Have you heard of LT-SPICE? Has anybody heard of, no? LT-SPICE? Okay, LT-SPICE is what Mike worked on before that when he was with another company. Qorvo is the company that offers QSPICE. That's where the Q comes from. Mike Engelhardt is known as a circuit simulation guru and has been developing simulation tools since 1975. So he created QSPICE as a more advanced and faster SPICE simulator, building on the legacy of his earlier project, LT-SPICE. Okay, so we know where the Q comes from. What is SPICE? SPICE stands for Simulation Program with Integrated Circuit Emphasis. It is a type of computer software used to simulate the behavior of electronic circuits. And it allows you to model and analyze circuits before they are physically built, helping you to identify any potential issues and optimize your design. So how does it do that? Through circuit simulation, SPICE software models electronic circuits using mathematical equations. It predicts how the circuit will behave under various conditions, such as different input signals and component values. There are other products out there that offer SPICE packages that are free. LT SPICE was originally created by a company called Linear Technologies, which is where the LT comes from. And now it's owned by a company called Analog Devices. It is also free. PSpice by Cadence Design Systems, NG SPICE by SourceForge, HSpice by Synopsys, and I thought I'd mention IS SPICE and MicroCap. I'm not too sure where they come from. So other not so free packages that you can get, there's one out there called Proteus by Lab Center Electronics. The base product starts at $685 and can go up to the high-end model for $8,622. Very expensive. The nice thing about the Proteus package is it covers these other products. ARM, it can simulate ARM, Arduino, Atmel, Motorola, I think that's NXP, TI, and I think it's MicroPython. So, yeah. There's another company out there that is not free. Another package is not free. It's called NI Multisim from National Instruments. The subscription price starts for the base model $879 a year, and for the high-end model $2,274 a year.
That's actually where I first used SPICE.
That's probably where you first use it?
Yeah.
And if you wanted to purchase it, it would be the low-end product is $3,000, and the high-end product is almost $8,000. So if you have that kind of cash hanging around, and it's a really nice program. It is really nice.
Is this based on some open source library, or is that because they're all called SPICE? Is there something underneath which is reused, or is that just?
Yeah, I'll tell you a little bit of history about SPICE coming up. If you want to read a little bit of more history, there's a short synopsis at this website here. So in 1960, at the University of California, Berkeley, the students there, Larry Nagel, along with his instructor, wanted to build a program that would model electronic circuits. The very first model they came out with, they called it CANCER. And it stood for Computer Analysis of Nonlinear Circuits Excluding Radiation. So I don't know where they got that from. So later on, in 1971, the same person working under Professor Donald Peterson rewrote and renamed CANCER to its present-day SPICE, Simulation Program with Integrated Circuit Emphasis. That's when SPICE 1, the very first version was written, and it was written in Fortran, and it was released to the public domain. So anybody could build on it, and these companies did build on it and have their own product. So did these, but of course, they're not cheap. Oops. Next slide. So my first exposure was in the 1990s. Does anybody remember Electronic Workbench for Windows? It's kind of like Proteus in a way, but it was back in the 90s. And it's now known as NI Multisim. It first originated as an educational tool for teaching electronics. It was developed by Interactive Image Technologies in the early 90s. It was a hybrid simulation tool for both analog and digital circuits used by colleges and universities. Later on, the company was bought out by NI Multisim, and yeah, that's where it became NI Multisim right now. So, of course, the product switched hands. It went from interactive image technologies to, who was it? Oh, it was bought out by National Instruments. So anyway, it's still around. Electronic Workbench is still around, and it's up to version 5.12. If you want, and it is free, so if you want to download it, it's a pretty good educational tool. So you see, you could do LED readouts. You can hook up 7400 series chips or MOS chips. You have a logic analyzer that you can hook up to it. And the real nice thing about this one, you could put a switch in your circuit, put a little switch in your circuit, and you could assign it a key on your keyboard. So if you hit S, that switch will toggle, and you could see what happens. Really nice.
I think
So
it's
if you want to download it, there's the website for downloading if you want to get it.
I mean, it's very cool because we are grew up in the 80s, I guess, or before, 70s,
Yeah,
I don't know.
yeah.
And it was very common that you would buy these circuits, CMOS circuits, build your own computer with that.
And they had a pretty good, they probably even have a better variety of integrated circuits that you could use in your simulations right now. So how can QSPICE help you? Well, advanced simulation capabilities. It could provide accurate power dissipation calculations, mixed mode simulations, improved numerical methods, enhanced design process, the faster simulation speeds, user-friendly interface. It has a model generator, custom C++ integration, also Verilog, which I'm not going to demonstrate, but it's about the same as the C++ one. Also has improved power management, enhanced performance, reduced design time, and better reliability. All right, so dish out your money, let's get it. Unfortunately, QSPICE is free. So, and there's the website you can go to if you want to download it. These are the system requirements: Windows 11, 64-bit edition, or Windows 10 with 4 gig RAM, 16 gig recommended, at least 16 gig for disk space for simulation. So let's see an example. Who remembers the 555 timer? That's an oldie, right? So here's the guts of the 555. It's a little 8-pin chip for timing. You could configure it for timing or a one-shot multivibrator or a stable multivibrator. So you got all these transistors and resistors and everything inside. That would be the analog version. You could probably build this in the simulator. There's no problem with that. But we're gonna, oh, by the way, you know where the 555 comes, right? Comes from? Right there. 5K, 5K, 5K.
Yes, because it's a comparator step.
Right. 5K resistors, all three in series. Yep. Okay. So we're gonna take a look at this one, where we have mixed. We have some comparators there. We have a flip-flop. We have an output buffer. We have a transistor. We have some resistors. So we have a mix. We have some analog, some digital circuits. I'm going to put it together. and see what we get. And we're going to try it out with this circuit here. This is a stable multivibrator. So you put a couple of resistors there and a capacitor. This, they recommend you put that in there, but it doesn't really figure in the calculation. So what I'm going to use, so this is what I'm actually going to build, or what I actually built to model the one that we had before. So I have, from QSPICE, I'm going to grab a couple of comparators and use those, a generic NPN transistor, a buffer, and I'm going to use 2 NOR gates as the flip-flop. So I'm going to hook it up to have R1 as about 5K, R2 another 5K, and a 1 microfarad capacitor for C. And if you do the calculation, it comes out to about 96 hertz.
You're not going to prove why these calculations are right now.
Pardon?
You're not going to prove why these are right now.
I'm not going to do it now?
No, I don't want to.
You want me to do it? I can do it right. I can do it right now. So let's see. So there it is. We have our 2 comparators. We have our 2 NOR gates as the flip-flop. You can see where the Q and the Q naught outputs are. Here's our 8 pins going all around. Here's the entire 555 here. So what is this gibberish? Tran means transient. So these are directives that you give the program. It follows these just like you would give MicroPython, a Python program. So you're telling it, you want to run a transient simulation for 200 milliseconds. So for 200 milliseconds, we're going to see what happens. We're going to plot V-trig, which is the voltage right at the capacitor. We're going to plot VQ, which is the normal output. We're going to plot V out, which is this one here, which comes through the buffer from Q naught. And then we're going to measure, we're going to measure the time from the first rise time of V out, the first time it goes up, I'm sorry, the 19th time that it went up, to the 20th time that it went up. That way we can get the period of our signal. Then we're going to take 1 over that to get the frequency. So we're going to do all that and see what happens. Now, you're probably wondering why I'm taking the 19th and the 20th. Is because as soon as you start the simulation, it takes time for it to settle down. So I'm going to wait for the 19th and 20th when it already settled down. So we're going to hit run. And there we go. Here's the capacitor. Starts at the high voltage, and then it's discharged, and then it charges, discharge. And you can see, here's Q, goes low, then it goes high. So when it's high, out is low. So that's the 2 outputs of the flip-flop. So what I'm actually going to do is measure it from, let's see, the 19th. So this one here to this one here. So that way we'll get the period, and then we'll do 1 over that to get the frequency. Whoop, what happened? I can see it already did the math for us. So it measured QP, which is the period of the 19th to the 20th rise time, and it comes out to about 9.5 milliseconds. 1 over that will give us 104 for the frequency. What did we calculate? 96, right? Why is it so far off? Oops. So it was off by about 9%, because we calculated 96, but we got 104.8. So we're not exactly there. Why so far off? Well, the reason is I'm using parts that I got from the bin. These are not exactly what's going to be inside of a 555 timer. This is inside a 555 timer. It's close, but it's not exactly the same. So what's the lesson here? The lesson is the more accurate you make the component model, the more accurate your simulation is going to be.
I actually remember the reason why I started looking into SIM is because my professor wanted me to make a standard trigger. So part of that was because the Zener diodes that were already included in multi-SIM weren't compatible with this current diagram.
Mm-hmm.
So I have to model that component exactly to its specifications.
Right.
So the model on the left is not as accurate as
Yeah, the comparators could be a little bit off. The buffer or these could be a little bit off. It can't be exactly what we have here. Here's the threshold comparator. Here is the trigger comparator, this section here. Here's our divider. Here's our flip-flop. And that's our buffer there. And the buffer feeds back to our open collector at the discharge pin. So it's not exactly the same.
So who created this model? Is it like a template that you...
This here?
No, the other one.
Oh, this one, I just created it from some parts that I got out of the bin. So, but let's look at something else.
Even if it was correct, temperature also makes a difference. I mean, these models, it's the capacitance of the wires, temperature, everything.
Yes.
I mean, even if you buy the same chip twice, you're not going to get sometimes the same frequencies. So because there's still production, inaccuracies.
Okay, so this circuit here is the same setup that I had before. Here's the 5K, 5K. Here's your 1 micro. VCC of 5 volts. We're going to look at it for 200 milliseconds. Plot V trig, again, capacitor voltage. Output. We can't look at the Q because it's inside there somewhere, so I can't get to that. So anyway, I'm looking at just the output, which is here. And then I'm going to do the same thing, measure the rise time, but this time on the 18th and 19th rise time, and then calculate what the frequency should be. So there we get the same signals. So when it does the calculation, we get about 10.4 milliseconds, and it comes out to 96. A lot better, huh? Why is this one better than the other one?
Because the model is more accurate.
Model is more accurate. And actually, this one came, if you go to the parts bin up here, behavioral, analog, there's the model I used, right from the parts bin. Now, if you right-click on the model, if you right-click on it, tell it to show the symbol properties. Here's all the properties of this symbol here. And look at here, library file. It's got something in there. If you go over to that library file, it's got a whole bunch of stuff in there. You know what that is? That's the inside circuit. That's the circuit that's inside here. There's the actual model. Tells you a component, where it's connected to, VCC, and CONT pin. Okay, here's 555. This is, I'm just telling you where it came from, the analog bin. The subcircuit NE555, here are the pins, the 8 pins. Common, trigger, out, reset. I think that's control, threshold, discharge, and VCC. So this resistor is connected between VCC and control. And the value of that resistor is 5K. This is what's called the SPICE model. So if you know if you can get all of this and you plug it into into this program, it'll make a model for you. And we're going to do that later on. So back to our regularly scheduled program. So, more accurate the component model, more accurate the simulation. So the next one we're going to look at is the Atari TIA digital simulation, or at least a partial of it. And you know what the TIA is, right, Frank?
Yeah, that's my fault.
That's your baby. Okay, this is just one page of the TIA. It's a very old, big chip, and it has a lot of components in it, transistors. It even has a lot of repeated components, and it has a blow-up of what all of those components are. So it is massive. 5 pages.
One question. For the video, is it kind of analogic at some point to generate a video that connects to the TV set?
Oh, I don't know. He's the expert on TIA.
So the TIA was indeed the video chip that generates the video signal, but the main benefit was that you can have sprites. So at this point, video systems didn't have any memory for the screen. They would just paint the screen as a beam moves along the screen.
Right.
And there was some internal logic that basically just churns out the right pixel information at the right time. And this is kind of in between a proper sprite logic and something which is so rudimentary that you really just have to program it in a very awkward way. So they're basically just counters that at some point decide to put out the right pixels. And I mean, this is a very primitive circuit comparing to nowadays. But then we're talking about the early 80s or late 70s, I'm not quite sure. So this was still the most modern things they had. I mean, and people used to write games with that. So it does generate the video signal. It doesn't do the modulation, I think. For the modulation, you might have some other parts. But yeah, it generates a video signal, which is not unlike modern VGA signals, but at a much lower resolution, basically.
So anyway, the issues with simulating the entire TIA, there's 5 images of internal components. And like I said, even if it shows an array like this, it blows up what each one should be inside that array. So it is massive. Some components, we don't even know what their construction is like, their timing requirements. there's specifications. So there's a lot to it. So how do you tackle, or how do you, resolution. How do you eat an elephant? Does anybody know that one? One bite at a time. So we took a bite of this little section here. And we have the clock coming in, and we have something happening in here. We're going to take a look at that next. So this is what it looks like when we blow it up. You have an oscillator coming in. You have a couple of buffers, a couple of inverters, so it's just buffering the signal. You have 2 flip-flops here. And then you have another set of flip-flops right after it. So the first bunch of flip-flops have a Q1 by them, and they feed this next couple of flip-flops with a Q2. And then we have a little reset signal here, which goes to the last flip-flop and the first flip-flop. So we're going to look at that. We're going to try to simulate that. And this is what we came up with. Here's our clock signal. We didn't have to go through 2 buffers, certain inverters, because it's the same signal coming out. So we have the clock signal across the top. Here's our VCC going to these points here. The thing I didn't like about this is that every gate you have to give it VCC. Yes. You have to give it power. So I did give it power. All you have to do is change the node, tell it it's VCC, same as this node, and I just made the font really small so you don't have to see it. Okay, and then this is our reset signal, and our reset signal goes from 0 to 5 volts, and it rises after 1 microsecond. And this is the rise time, 0.1 nanosecond, fall time, 0.1 nanosecond, and the pulse width for the first pulse is 1 millisecond, the period is 2 milliseconds, and this tells you how many pulses, 1 pulse. So for 1 microsecond, we're only going to get 1 pulse. And then our clock is going to be a little bit slower. So.
Can I ask a question quickly? So when we look at the 2 diagrams, this one looks really nicely drawn,
Mm-hmm.
perfectly, and the other one looks like someone drawn by hands. Why is that?
Which one?
The one on the previous
Oh,
slide.
they probably did draw it by hand. They probably did.
The one that says divide by 3 and things like that.
This one. Yeah.
This was 82, no? Like 84 when that was drawn.
Yeah. And they probably did draw it by hand. And it's very old, so this probably fade. Look, it's got fading here. So.
Electrical and mechanical design used to be by hand, everything, so.
Yeah. Bobby wrote it out on a napkin, you know. So.
So this was before QSPICE.
Way before QSPICE. Yeah. Okay. So from this, it says it's a 1/3 clock frequency generator. So we were thinking it takes this clock pulse and it divides it by 3 to get this output over here at PP. So we're assuming input is at the clock here and output is at PP. So we tried it out.
If we were to prove this mathematically, we would just be dividing the clock by 3, right?
Yep.
That's a cheap one. That's actually our emulators.
So anyway, here's the 5 pages with the drawings in there. And they're massive.
Same size.
Yes, they're big. So,
And by the way, this is small. If you compare it to modern circuits, this is tiny.
yeah. So here's our circuit. And we're going to run it for 50 microseconds. where's our clock at? Our clock is only 1 nanosecond. So after 1 nanosecond, it's going to jump up for 1 nanosecond, and then that's it. So we're going to reset after 1 nanosecond, and then our clock is going to be running after 1 microsecond with a rise time of 0.1, I think that's microsecond or nanosecond, 0.1 nanosecond fall time, 1 microsecond pulse width, and then the period 2 microseconds, and it's going to run 100 pulses. And then what we're going to plot is we're going to plot V clock, which is along the top. We're going to plot, is that VVR? Oh, the reset, our reset signal. We're going to plot Q1, which is from the first bunch of flip-flops, and then Q2 from the second bunch of flip-flops, and then VPP, which is we're thinking is going to be 1/3. So let's run that, see what happens. And there we go. Here's our clock pulse. Here's our reset signal, very small compared to everything else. And then here's Q1. This is the first bunch of flip-flops. This is the second group of flip-flops. Here's VPP. So we can come up here and try to measure all this, but let's let QSPICE do it for us. So.
How long did it take you to get this circuit right? Is it easy to make mistakes?
No, it's actually not that hard. It wasn't that hard. So for the trigger, anyway, oh, this is the clock. This is the clock signal. So we're measuring 2e minus 6, what, 2 microseconds? 2 microseconds for the clock. So that's 500,000 hertz for the clock. So the output at PPP or PP is 166,667. Is this 1/3 of that? Hey, I think it works. So, I guess we were right then. This is the output, which is 1/3 of what our clock is. So we figured out one part of the TIA, right? Well, I'm not going to do the rest, so I'll let Frank do the rest. That's his baby.
We can give a prize the end of the year. People have already done that, so.
Oh, I'm sure.
But not with QSPICE. I haven't seen anyone who's trying to do it with QSPICE.
The QSPICE? Hmm.
Yeah, there might be 1 or 2 people, but there's very little on the web.
Well, if you could figure out Verilog or how to write it in the C, then you could just write it in C.
Yeah, I mean, yeah, I can say a bit more about that later.
Okay, so your mind is blown. What else can QSPICE do? Well, how about creating your own hierarchical devices? What the heck is a hierarchical device? It's where you take a circuit that you build, like this, and you stuff it in that box.
This was already in the timer, no?
Yeah. There's your RS flip-flop that we could plop right in there. So you create the device you want to, the circuit you want to build, create the box, give it some inputs and outputs. Here's our reset, set, common, B+, Q naught, Q output. Right-click on the box, and then it'll take you to this window, and it'll show you a blank box with the same outputs that you just generated. So you go back to your original one, copy the entire circuit, and then paste it into that box. Connect the wires all the way to the port, to each port. And you go back to your original page, the original window, and your electrical box can be saved, and you could use this into any designs you want to use in the future. Okay, you want me to show you, right? Let's see it. Okay, I already created the box. I already gave it some ports. But if you wanted to do that, I can show you how to do that. Just go anywhere on the workspace, right click, and go down to draw hierarchical box or hierarchical entry. And it'll give you a bullseye. You create your box. And it seems to always give it an X something. And I think that means there's something inside that box, hierarchical device. And if you want to give it some ports, right click, add a port, place it there, add another port, go to the port you created, right click, or you could just better yet, you could just double click it and it'll let you give it a label. So I gave it a R for that. Let's say Q for that side. So that's really what I did to create that other little box there. So we're going to get rid of this and blow this one up. Okay, so once you have everything set the way you want it, right click on it and say enter schematic. It's going to say one doesn't exist. Do you want to create one? Sure. And there's that box I showed you before. Now, what circuit are we going to use to put in there? Where is it at? Okay, there's my circuit that I want to put in there. Copy the whole thing. Placed. Then you're going to want to move the pins over to the ports that are already existing there. Oops. All right. So then when you go back over here, everything's embedded into this box. So I have a demo already made. So this is the one I created. I didn't want to go through the whole mess. So anyway, this is the one I created before. If you right click on it, oops, nope. I should have created the other one. Anyway, anyway, it'll be inside the box. So I should have created the whole thing. But anyway, this was the test circuit that I was going to use it on. And this is actually coming from the bin from the behavioral under digital. This is a real flip-flop. I forgot to create the other one. So anyway, believe me, it works. It works fine. Okay, what about this C++ and Verilog that you heard so much about? Well, to embed C++ into your design is about the same as creating the hierarchical device that you did before. First, you create a box. You give it an input and an output. And you give it nodes, give some labels. Then you want to right-click on it. This is important. You want to right-click on it, and you'll see this box. You want to select symbol properties. And when you do that, you want to go to this, this drop-down, symbol type. If there's nothing here, it won't allow you to select. It won't allow you to select a C++ or a Verilog, or it won't allow you to name the ports input or output or Boolean or such like that. So you want to go down here and select DLL. And when you do that, then you right-click on each port. When you right-click on each port, you could tell it, I want this port to be an port type will be input or output. Then you have to click on it again, right-click on it again. You want to tell it, is it going to be a Boolean? Is it going to be a signed, short, unsigned? Once that's all good, right-click on the box and then select Open C++ Source. When you do that, it's going to say there's no file for that. You want to create one. You want to create a template. You hit yes. When you hit yes, it's going to give you more options. It's going to say in your template, do you want us to create a structure in your template? Do you want us to define display in your template? I'm going to use both of these. I'm going to use the structure and the display, and you'll see why. So you want to see an example. Okay, let's go look at an example. So we right-click, we select hierarchical device, create our box, now if you right-click it and you ask for the symbol properties, there's nothing up there. So if you right-click it, there's no C++. You can't select any C++ or DL or Verilog. Not until you select DLL. So let's give it a port anyway. Add a port. Add another port. If I right click on the port, it won't give me a choice of saying this is an input or an output. Again, not until you select DLL. So let's go over there and select DLL. Now we can select input or output. Port type, input or output. Data type, you have a big selection there. So what if I wanted to see the C++? Yeah, it's right there. If I want to open it, oh, it doesn't like the module name. So if I ask it again, it says it does not exist. Do you want to create one? You hit yes. Well, it doesn't like that I didn't name the pin. I didn't tell it was an input or an output or what type it is. So it does require you to do a lot of things before you can see that C++ file. So we're going to tell it this is our input. We'll even name it in. This is going to be a Boolean. We're going to give it the name out. This is going to be an output. And it's going to have a data type of float 64-bit. Now, what if we hit open C++ source? It's going to say it doesn't exist. Do you want to create one? Yes. There's my options. So I'm going to click those two. But I don't have to. I already made one. So we'll take a look at that one. So there he is. He's got an input. He's got an output. If we click on one of the inputs or outputs, the shaded one is the one you selected. Shaded one is input, so he's an input. What's his data type? Shaded one is Boolean, so he's Boolean. What about the output? Shaded is output, so he's an output. Data type, float 64, right? So we right click on this. Let's look at the C++ file that's behind it. And there he is. And I believe when I created this one, it only gave me like one or two of these include files. So I had to add standard I/O and the rest of them, the math one too. So here's our structure it added. Wait, that's not the one. Here's the structure. And I added this variable called state. And when you create the template, it's going to leave this section after implement module evaluation code here, everything after this is going to be blank. That's what you create your program there. So what it's going to do is it's going to look at state, the variable that I made. And it's going to say if it's 0, we want to say the start of simulation, state goes from 0 to 1 at how many nanoseconds into the simulation. New line. And then we're going to change state to 1. Okay? Then it's going to come through the loop again, and it's going to say state is now 1. But it's also going to look for the Boolean on the input. If our input goes high, it's going to display this. First input state change detected. State goes from 1 to 2 now at how many nanoseconds? Give us a new line, and then state goes to 2. Now in cases 2, if our input goes low, it's going to say the second input change detected at input went to 0 at how many nanoseconds? State goes from 2 to 3. So state goes to 3. And this was in there before from another program I was working on, but I just commented it out. So what happens when the input goes high? If the input goes high on your Boolean input, then it's going to say make the output multiply by the input, which is going to be a 1, times sine 2 meg, oh, what is that, pi? I think this is the symbol for pi, so 2 pi, 1 e to the 9. So it comes out to 1 gigahertz sine wave. So it's going to generate a 1 megahertz sine wave every time the input goes high. So let's see what happens. Oh, after you're done putting your program in and you want to compile it, right-click anywhere, select compile. Notice what it says right over here. New component X1 DLL created successfully. So if everything goes good, it's successful. So I just added this circuit over here, but it doesn't really need to be there. We're just going to look at the output here, which is going to be our sine wave. So pulse coming in is going to go from 0 to 1. So that's our Boolean input after 10 nanoseconds. Okay? 10 nanoseconds is going to go high. Rise time, fall time, 1 picosecond or whatever, picosecond. It's going to stay high for 50 nanoseconds, and then the period is going to be 100 nanoseconds. So this is tied to the pulse. Actually, if you click on this, you'll see there's a little tether. See that little tether there? It's saying that belongs to that. We're going to run a transient analysis for 200 nanoseconds. We're going to plot V in, which is our Boolean input, plot V out. Let's see what happens. What do we expect to happen?
Sine wave.
When the input goes high. Let's try that. There you go. Here's our input. Goes high. When it goes high, we get a, what was it, gigahertz? How many gigahertz of signal?
1 gigahertz.
Yep. When it goes low, turns off. When it goes back high, turns back on. So the reason I selected that display to be added is for this. It's going to give me little debug messages to this window. I don't know, for some reason, the first time I run it, it doesn't work, so I got to run it again. So let's run it again. And there you go. Oh, I got to get this out of the way. So there you go. Start a simulation, 0 to 1. State goes from 0 to 1 at 0 nanoseconds, right? First input state change detected. State goes from 1 to 2 at 10 nanoseconds. 10 nanoseconds, right? Second input state change detected. Input went to 0 at 60 nanoseconds. So it goes up at 10 nanoseconds, stays up for 50. There's our 60. And this tells you the total elapsed time for the entire simulation was that short. Everybody see how that happened? Okay, smarty pants. So what if we need a device that QSPICE doesn't have in the parts bin? We write C++ code to make one, right? Or we find a model description. And some manufacturers like TI, they post SPICE models of their products. If you look around, you could probably find them. I got lucky and I found a 741, LM741 model. Everybody know what this LM741 is, right? Yep. So if we wanted to use that SPICE model, the description for a 741, how can we use it? Open SPICE, QSPICE, I mean. We open the SPICE model description, and I think this one comes with a .lib, so .library. And you could use Note++, I use Note++, and you can see it's all written out just in the text file. In the document, select everything in the document, hit Control-C to copy everything. Go over to your QSPICE workspace and hit Control-V to paste it into the workspace. And when you do that, you get this. And it says, shall a symbol be generated for the sub-circuit LM741? Yay. Do you want us to create a symbol for it? And look, there's that same stuff we saw before for the 555. This is the actual description of the insides of the 741. So you say yes. And then you get this. That doesn't look like a 741. What are these numbers all about? So you go back to the description, and it tells you what they are. 1 is the non-inverting input. 2 is the inverting input. 99 is the positive power supply. 50 is a negative power supply, and 28 is your output. If you want to use it like this, that's perfectly fine. It'll work. But we want it to look like an op-amp, don't we? Doesn't look like an op-amp to me. So what we have to do is make it look like one. So first we take what we got. We put the nodes where they should be. I think this was the non-inverting and the inverting. Maybe I got it mixed around. Anyway, this is VCC, this is common, that's the output. So we orient them the way they should be. And then we get rid of this crazy box here. We make a nice op-amp triangle, and we give it the plus minus inputs it should have, right? How do we get there? Arranging the inputs is easy. That's drag and drop. To change the shape of the outside shell, this requires the use of something called the new symbol editor. So you go to QSPICE, click on File, there's new symbol. You click on new symbol, and this window pops up. Looks like a bullseye. You go back to the part you created, click on it, copy it, go back to the new symbol editor window, and Control V to paste it in there. So there he is, he's inside. Now I do have the ports already where they should be. Next thing you do is click on the shell, get rid of the shell. Then you right click anywhere in the workspace and it'll give you a tool, the triangle tool. Align the triangle with the inputs and the outputs. Now to make these numbers disappear, you just want them to be hidden, invisible. So what you do is when you double click on it, you'll see these dots show up. Double click on the middle dot and then click away somewhere and it'll tell you, it'll come up with another message. And it'll say, do you want this symbol to be invisible? Yes, we do. Next thing you do is after you get everything invisible, you want to right click on the workspace and then click the line tool. You want the line to go from the positive to the common. It's not really good, it's not a wired, it's just a line showing that there's a, you know, it's not really a wire. It's just for looks. Okay. Now you want to right click again and select the text tool and then create your plus and your minus input labels. Note we're not changing the port label which had the numbers before. Those are invisible. All we're doing is putting some text. So we're going to put the plus and minus right on the inputs. And after you do that, you have to remember to click on the text that you created, the plus and minus, and tell it it's a comment. If not, it'll think it's a SPICE directive, and it's going to say something wrong there. It doesn't like that. Once all that is done, Control C to copy everything that you created in that window. Go back to the regular workspace, and that box that was there, you could just delete that and then just paste this one in its place. And then you're all done. So let's try that out. Okay, here's the, I'm going to open that with Note++. Here's the model. Oh, what happened? Did I lose something?
Maybe it's the connector.
Oh, okay. So I'm going to open it with Notepad++. And there's our model right there. So I'm going to select everything. Select all, copy, go into QSPICE, Control V, and there it is. It's saying, do you want to create a new device? We say yes, and there's that ugly yellow box. With numbers, we don't know what they mean. So we're going to put this one below, put this one above. I think 99 was, 1 is non-inverting, 2 is inverting, 99 is positive, 50 is negative. So this goes up here. 50 is negative, it goes down here, and 28 is our output, right? So everything's in place. So we go to File, New Symbol. There's a bullseye. So we go back to that ugly box again. Copy it. Go to the bullseye, paste it. Get rid of the shell, right? Right click, triangle. Okay. Okay. Now we select the line tool. Put it from here. Oops, I think I did it crooked. Now, I gotta move this guy over. Anyway, that's kind of messy. I'm rushing things. So if you want to make these labels invisible, double click on them, you'll see those dots coming up. Let me blow up that a little bit. There's all the dots. If you double click on that middle one, it says you want it to be invisible. Say yes. Okay, select the text tool. We want to put a minus here. Text tool, put a plus here. Okay. Right click it, tell it this is a comment. And you can see it turns a little blue. Right click that one, comment. there you go. Our op amp is ready. You can copy everything. Oops. That wasn't right. Go back to our other window. Get rid of this guy. It didn't copy the whole thing. Let's go back there. Yeah, did it again. All right. Something's not right here. No, that's not working. Oh, there we go. Okay. So it worked. Actually, I got too many. So there's our 741. If we want to use this, save it, we can use it in a model, and it should work. I have one. I think I have one already created. Let me make sure that I do or not. Yes, I think I do. So I'm going to close this one out. Close this out. And I have one. I forgot to save it again. This is a model from the bin, but it should work exactly like this model does. So, any questions about that? So, in conclusion, there's a whole lot more to QSPICE than I covered here tonight. There's audio circuits. QSPICE even comes with a bunch of audio examples. It comes with a bunch of examples in different mixed mode audio examples. For those of you who are into audio circuits can be simulated. You can work on the frequency response of your designs using Bode plots. This QSPICE has even been referred to by Mike Engelhardt as being a beta of sorts. And there's not a whole lot of parts that you get in the parts bin. If you've ever looked into LT-SPICE in their parts, there's like a ton of different models you can use in there. LT-SPICE has been around for a lot longer than QSPICE has. But it's getting better. It gets updates pretty frequently. So if you want to use QSPICE, they have a forum. There's the forum. There's the connection to the forum if you want to go there. And they can help you out with anything you're working on. So hopefully QSPICE will get better and better, and it'll help you with your designs. Any questions? Yes.
Just wait for
Okay.
Sorry.
Excuse me. You said it has like some of the components are audio signal generators or something. Is there like a, are there directives or ways to hook up the output to, like output signals to speaker or something like that?
This is the bin that they have for all the parts. They even have some parts in alphabetical order. You have some voltage source. It even shows you a little symbol down here of whatever you select. So you have a behavioral voltage or current source, a resistor. Under C you have different capacitors. For D you have diodes, Schottky, you even have LED. And then down here they have behavior where you're going to get, where they have a list of analog, like a latch, D to A converter, oscillators. This is, where is that amp? Oh, here's the 555. Op amp, generic. This is the one I used in the design for the 555. Yeah, phase detectors. So, I don't know, does that answer your question? Or?
For, if you have a circuit that like outputs a waveform, can you like sample that and like use some kind of directive to send the waveform to a speaker or something like that?
Oh,
To listen
you mean
to
using this?
Yeah.
No.
Okay.
You can't do that. No, sorry. That would be nice though.
I'm sure you can write a script or something.
Yeah.
Yeah.
Dump a wave file or something.
MicroPython.
Yeah, maybe a MicroPython, yeah. So, any other questions?
Thank you. Hi, so first question, is this all in Windows? Is there any Linux ports for
Pardon?
QSPICE? Is there any Linux ports for QSPICE?
You need what?
Linux version?
Yeah,
Linux.
Linux?
Linux.
No, right now all they have is Verilog and C++. That's all
Okay.
really- Yeah. Yeah. So who knows? Maybe in the future they might add those functionalities. Yeah. I don't
Okay.
think even LT Spice doesn't even have that. So
Yeah, I don't
Yeah.
think it's LTSPICE. I remember there's one version though, but I don't remember which one.
well, you did, and I mean, if you have the money, you could pay for Proteus,
Yeah.
which you know they do cover a lot of different devices. So,
Exactly.
but that's expensive.
Very expensive, yeah.
yeah, it is.
Thank you.
I have more questions.
Any more? Okay.
I might have one question. Sorry, I need to just. Sorry, it's my wife. So, I mean, when you integrate kind of C++ with analog simulation, I suppose that the simulations are accurate in the sense that they model behavior of components, maybe even of wires. So you have resistance, reactance,
Mm-hmm.
timing, and all that stuff. But when you put it in the context of a digital simulation, you're not providing that information. Or is it possible also to integrate sort of more sophisticated behaviors? So how does it combine digital and analog simulation?
Well, it all depends on the model. So, I mean, if you have a good model description, then you could have it model just about anything. For instance, if we had a transistor, where's our transistors at? Under Q. Show symbol properties. Now this is just the generic one, so it's not going to have a whole lot of stuff in there. But if you right-click on it, you can go to the selection guide, and you could pick any one of these models up.
I see. But this is from the bin, right? If you have a C++ simulation and you want to have something which behaves like a capacitor, for instance, can you do that in C++, or is it?
I'm not really a programmer. I'm not much of a programmer.
I think it's more an issue how you combine digital and analog behaviors.
If you knew the mathematical model, then you could do that in I'm sure you could do that in C++ then.
Yeah, I mean, there's many different ways to define behavior of circuits. I mean, as you already mentioned, one is impulse response, and another one is in Verilog. You don't usually model that because you're working on this abstract level. So you either have voltage or no voltage. And it has a few other states with this high impedance, low impedance states and things like that, but it doesn't really model reactance. And it's really interesting because when you look at the circuit from the TIA, on page 5, on the top left corner, it actually tells you the characteristics of all the gates. So it uses NMOS.
Right.
But each transistor is different, so they have different properties. And so it's interesting because how deep are you going to simulate it? If you just take the digital model, then you only get a digital simulation, but then using QSPICE, maybe you can go deeper and actually consider timing as well. So what's the maximum clock you can use? Because there's a point when the clock is too fast and the gates are not responding because NMOS sometimes responds slowly. It is especially, it responds slowly because you have pull-ups everywhere with NMOS. But I really love this talk because it's really about the embedded systems engineering sometimes have to worry about, because it's not about digital 0 and 1s, it's about the voltages and the properties of these elements.
I'm going to change this transistor to just a random one, to that one right there. Now if you look at the properties again, right, you just hit it. I think they do have a file that gives you all of the, I think there is a file, but I don't know how to get to it. But it tells you all the different parameters for this particular transistor.
So in analog technology, we always have these parameters, and they are really related to the manufacturing processes, to the size of the different layers, and Thanks. It was really interesting. So I don't know if there's any more questions. So let's thank Sid maybe again for that really brilliant talk. Thank you. So I think that was the...
Here's some of the parameters for a transistor.
Nice.
In the help file.
Yeah, even temperature. I mean, if you change the temperature, it changes probably.
You could change the temperature coefficient, so how it behaves to temperature.
I see.
Flicker, parasitics.
Which is very interesting with instruments when you do synthesizers, because they used to behave differently when they're warm and cold. And
beta for the transistor, so the beta for the transistor could be different from one state to another.
Wow, there's a lot of parameters there. My God.
Yep.
Yeah.
So there is a text file, I'm sure, with every different model of transistor in there. I just haven't been able to find it. But I'm sure it does fill in all those blanks there.
Yeah.
Okay.
Cool. Awesome. Thanks so much, Sid. And I think we will hopefully have our next ESG meeting, I hope maybe in July or August, because also I will be away on holiday. But if you like to give a talk, or Sid, you like to give another talk, QSPICE too. So we need to find some more talks, maybe Danielle, and I'm sure David. You can give 2 talks as well, or 3 if you want. So I try to get more people to also engage with this, and maybe we can upload the files on the GitHub page. I'll
Well,
also,
like I said, I do have it in Spanish. So if anybody wants to see it in Spanish, I do.
that would be really useful, yeah.
I sent you both versions.
I will try and upload them.
Okay.
Yeah.
Share the code, the discount code with everybody.
Could you do that?
Okay, yeah, sure.
You give it to me, I can put it on the...
I think I sent it to you through WhatsApp, but I'll send it to the WhatsApp group. I'll send it over there, and if you guys want to grab some tickets, you are welcome to. If not, well, that's your loss, because this guy's going to give a pretty good talk. That's all. Thank you. I'll send it over.
Thank you so much. I think we have... Do you fancy a beer? Okay, I think...